We're gonna talk about now SN1 reaction. That is first order nucleophilic substitution reaction. First order nucleophilic substitution reaction. Let's say we have a nucleophile Rl and which is dissolving in solvent, and we have a nucleophile over here. So when it gives us RNU plus L minus, leaving group and nucleophile. So how does it follows the mechanism? Which kind of mechanism does it follows? So let's see mechanism. And mechanism, let's understand first. We have RL. RL has delta positive, L has delta negative. So it is actually a slow RDS. And first step will be slow and it will be RDS. Slow steps are RDS, rate determining step of the reaction, and it breaks into cation and anion. In second step, the cation get attacks with the nucleophile and forms RNU. Okay, it forms RNU. Now, what are the characteristics of these reactions? Characteristics of this. What are the characteristics of this reaction? So, the characteristics of this reaction is first, we have rate. Rate equals to K times RL. It is K times first order nucleophile. Second, it is order equals to 1. The order is equals to 1. Third, it is known as SN1 reaction. It is akin to RL because it is elementary reaction. In chemical kinetics, we generally study what is the elementary reaction and what is the complex reaction. So it is a single step reaction, first step. So it is elementary reaction. The SN1. Fourth, we have rate is directly proportional to the stability of carbocation. Stability of carbocation, it is the rate. Fifth, rearrangement of carbocation is possible. Rearrangement of carbocation is possible. And sixth, how do we compare the rate? The 6th point, let's say we are writing, let's say, rate comparison of SN1. Let's say compare the rate. Compare the rate of SN1. First we have CH3Cl, then CH3 CH2 Cl, then CH3 CH3 and Cl, and CH3 CH3 and Cl. So here we have seen already that the rate is directly proportional to the stability of carbocation. So it is 3 degree carbocation, it is 2 degree, it is 1 degree, and it is methyl carbocation. So this should be the order, right? Second, pH CH2 Cl, then pH CH2 and Cl, then pH2 CH2 Cl and pH CH2 Cl. So then that will be the order because this carbocation is going into the resonance with it. Third, we have Br and we have this bromine. Due to dancing resonance, sigma resonance, carbocation is very stable over here. Fourth, we have here we have bromine. Here we have bromine. And here we have bromine. So first, if bromine goes, then carbocation will come here, and come here. So in that case, it will be non-aromatic, it will be anti-aromatic, and it will be aromatic. So that will be first, that will be second, non-aromatic will be second, and that order will be third. Now let's take more questions. Let's do fifth question. We have OTS and we have here OTS. So the stability of carbocation here, the carbocation will come here and will come here. So it has more the steric 60-degree angle. It should be 120-degree and it is already a 120-degree angle in second case. First case that angle is 60-degree and that will be carbocation. So a lot of angles stay on the carbocation. Instead of 120-degree, it is forming only 60-degree. So fifth, the second case is more stable. Sixth, let's try Cl, N, Cl, then H. So the oxygen and nitrogen both are having lone pairs. Here it will come positive charge, here it will come positive charge. So nitrogen will donate its lone pair to chlorine, the carbocation, with electronegativity order. We know it is fluorine, oxygen, nitrogen, then chlorine. So oxygen has more electronegativity, so nitrogen will having more electron donating tendency. So it is this order. So let's do the seventh problem, the last one. We have a Cl. Here also we have Cl. So it is carbocation here and carbocation here. Here not Cl, here it is Cl. So here carbocation. It is getting plus M, it is getting minus I. Obviously plus M is more stable, so it will be, it has more rate. So that was all about the rate of the SN1 reaction. Now we're gonna talk about the characteristics. Characteristics. Now characteristics. First, rate of reaction is independent on strength and concentration of nucleophile. How strong the nucleophile, it doesn't depends. It will form after it will attack after the RDS. Okay. Second, rate of reaction is directly proportional to leaving group ability and inversely proportional to the basic strength of L negative. Right? It will directly proportional to the basic strength of L negative. Let's solve some questions. CH3, CH3, then Cl. We have to identify the rate of the equation. Okay, rate of the reaction. Rate of the reaction. And we have Br. Here we have I. Then CH3, CH3. We have here fluorine. So good acid is are the good living group. So it is will first, second, HCl is the third, and HF is the fourth. And let's do the second problem. Here we have a living group OS double bond O. Carbon. Here we have a methyl group attached over here, and to this we have NO2 group attached over here. Okay, so NO2 has 1, then 2, then 3, because minus I tendency increases the acidic strength. Minus I increases the acidic strength, the good the acidic strength, good better will be the living group. It will be a better living group. Then third, PHCH2. pH CH2. Now it has this is the living group over here, and this is the living group over here. So which is the good acid? The second one is a good acid, so second is a good living group. Next question. Here we have chlorine. Here we have bromine. And here we have iodine. Again, good the acidic strength, better will be the living group. Fifth. Second is the better living group. Now, if we talk about this solvent, that's how we have compared the rate. But how does the solvent affect the rate? In that case, solvent. How does a solvent affect the rate? The solvent, we have carbon and we have chlorine. When it reacts with water, it does form this OH. Right. So the solution, this is called the solution. What happens? Chlorine goes, then there is a generation of carbocation. Then we have a lot of water. So water will attack over here. Now we have this OH, then H, a positive charge will go. It will go minus H plus and it will form the alcohol. So actually, we do not wish to solvate the carbocation. We do not wish to solvate this compound. Or we can say, if we use the polar protein compound, we do not wish to solve it. Means yes, we wish to solve it. I repeat, we wish to solve it this compound because H2 here act as a nucleophile, right? So polar protein solvent are favored. Because it behaves as nucleophile and form product. And behave as a nucleophile and form product. And directly form the product, so it behave as a nucleophile. Now, what is the most favorable? What is the most favorable condition? That is known as solvolysis. Most favorable condition is solvolysis. It must be first 3 degree or resonance stabilized carbocation. 3 degree or resonance stabilized carbocation should be there. Second, there must be a good leaving group. That is for the reactant. And for the solvent, it should be polar protic solvent, which must behave like nucleophile. So which must behave like nucleophile, so then overall reaction happens. Now let's talk about the stereochemistry of SN1 reaction. Stereochemistry of SN1 reaction. So in order to calculate the stereochemistry of SN1, we have CPH, then CH3, then CH2, then CH3, then Cl. We have CH3OH. Okay, obviously all the favorable condition are for SN1 only, right? So it will form SN1. First CH3, CPH, Cl, CH2, then CH3. First of all, leaving group will go RDS, then C positive, pH, CH3, CH2, CH3. Then it will form Cl minus. In second step, C positive, CH3, CH3, CH2, and pH. Now it is a free carbocation now. So H2O can attack from both sides. And H2O will attack from this front side also, from backside also. It has both the chances because it is sp2 hybridized. It is planar now. It is a planar compound, so it can attack on the both of other side. So when H2 will attack and H plus will go minus H plus, I am writing in a single step. So it will form CPH. Then here we have alcohol, not H2. CH3OH. Right, alcohol we have. So COCH3, then CH3, then CH2 and CH3. So it will forming a compound, stereo compound R and S, both the configuration we will be getting here. R and S, both the configuration we will be getting. So what happens actually when we have an intermediate forms like X, Y and Z? When we have a carbocation, a nucleophile attacks, a nucleophile could go from this side also, from this side also. So it forms two compounds like CNU, X, Y and Z, and CNU can be here X, Y and Z. Both type of compound it is formed in this form. Now the question solves some problems. We have here chlorine, then H2O. So it will form which compound it form. So let's solve the problem. So first of all, chlorine will go. Here we have carbocation. Now carbocation we rearrange. Here we have carbocation. Then here will be a positive charge. H2O will here. Now carbocation will rearrange here. And H2O will attack over here. Now the final conclusion, this product will form. So the finally ring expansion will take place and this product will form. Now what is the energy profile for SN1 reaction? Energy diagram of SN1 reaction. Energy diagram from SN1 reaction. Let's say we have I over here. So it will form transition state 1, then the carbocation will form, then Cl minus will attack over here. Cl minus will attack over here. So now how it will look like on scale? It will go like this, and it will be going like this. So it is transition state 1, it is transition state 2. It is slow step RDS, that's why activation energy is more. Here will be the, and this is the stable intermediate with the generation of carbocation which we are going to take place. And here when it is separating from the I minus is separating from delta positive and delta negative, and it is when the compound is formed. And it is when compound is formed, and when the chlorine will attack, it will form Cl minus will attack. We have this step, Cl minus will attack. When I minus will leave, it have transition state. When Cl minus will attack, we have transition state 2, and this is the intermediates we have, carbocation and the final product. So delta G of the reaction is actually negative. Delta G reactions comes out to be negative. Because of slow step it does form, and it is intermediate, that this is intermediate. So that's how we look the SN1 reaction.